Hello, I'm Danny Webster from Lime Microsystems, and in this session I'll be talking about in detail what the LimeSDR is and the various blocks inside it. So we're going to start off by looking at the analog part of the 7002 microchip, and then we'll look at the digital half of it, and then we'll just very briefly talk about the LimeSuite GUI and how to use the LimeSDR well. And then finally just a tiny bit about the FPGA on the LimeSDR. The 7002 is a second generation all CMOS transceiver with low power consumption of less than 2 watts. It's originally designed for the 4G femtocell and picocell market for home base stations, giving 64 CRAM OFDM, 2.5 dB noise figure, and handling up to about 15 dBm CW blocker. It requires external PAs for femtocell and picocell operations. There's also a PCIe version of the LimeSDR, which was designed for digital pre-distortion, and that has 50 MHz IF bandwidth and supports ADC and DAC speeds up over 100 megasamples per second. It also has high-speed digital interfacing. If we look at a block diagram of the LMS 7002, it can actually look rather frightening. So, well, let's just turn away from that rather complicated diagram and break it down into something a little bit more simple. Basically, the 7002 is a MIMO transceiver, so it can support up to 2 transmit channels operating simultaneously and 2 receive channels also operating simultaneously. Each transmit channel has 2 outputs, one for the low band and one for the high band, and each receive channel has 3 inputs, a low band, a wide band and a high band. And there's also 3 frequency synthesizers. This includes the transmit synthesizer, the receive synthesizer, and a clock gen for the digital system. So let's explore the details a little bit more gradually. The 7002, like many digital radio receivers, is based on the Homodyne, which was developed in the 1930s. It's often called the Zero IF transmitter or receiver, and it shares many similarities to the Hartley single sideband modulator. The inputs are an IQ signal, which, if you like, forms a vector description of the signal which you're transmitting. It has 2 frequency mixers, and then the outputs are combined. The synthesizers used in the Lime transceiver are a classic DDS type synthesizer featuring a voltage controlled oscillator, a feedback divider, a phase frequency detector with a charge pump and a loop filter, and a feed-forward divider. Typically, we would use a 30.72 MHz crystal oscillator as a reference, and we would achieve something like -90 dBc phase noise plateau. That corresponds to an integrated phase noise of about 0.5 degree at 800 MHz and about 1 degree at 2 gigahertz, which is fine for 64 CRAM. Typically, we would have something like 155 dBc far-out phase noise. So going back to our vector modulator again, we have now added a digital interface, so we have DACs driving the modulator, and we have some low-pass filters. So why do we need these low-pass filters? It's to actually deal with a problem called aliasing. So in a sampled system, we look at points on a continuous waveform, and these points are usually equally spaced in time, so that when we reconstruct this signal, we not only generate the signal that we want, but we also generate harmonics of the sample rate, and these are called aliases. And by using filtering, we are able to remove these. So one of the ways we can actually reduce these aliases in adjacent channels is by changing the sampling rate. So if we double the sampling rate, we can increase the space separation between the wanted signal and the various aliases components. And that means we can then relax the filtering requirement needed for the radio. And this in turn reduces noise and complexity. So we have a fourth order Chebyshev filter in the transmitter and a second order Butterworth for the high band. Another aspect of sample data system is quantized noise. Basically, the digital to analog converters and the analog to digital converters have a finite number of bits. So the quantized data is never really completely accurate. It's always an approximation to the grid of the data converters. So the 7002 has a 9-bit E-knob, so it can generate at least 9 bits of accuracy. So let's look at some of the problems with a very simple 3-bit ADC. So in a 3-bit ADC, there's 8 possible levels. So not all of these levels are normally used. So in this example, we're only using 7 of the 8 possible levels. Almost every sample point has some sort of error associated with it. And this error looks like noise when you look at this in the frequency domain. So the larger the number of bits, the better the signal-to-noise ratio of the final signal is. So typically with a 9-bit E-knob we get 56 dB dynamic range, and with oversampling we can increase that further. So let's have a look at oversampling and quantization noise. So as well as the aliases that we talked about, there's a broadband noise, which is the quantization noise from the data converters. And when we do the oversampling, we actually can push down this quantization noise, giving us better signal-to-noise ratio in the adjacent channel. So the LimeSDR is intended to work with a high level of oversampling. For example, in a 3G or a 4G base station, we would use a data rate of about 30.72 megasamples per second, and then run the TX at something like 245 megasamples per second, and the RX at 61 megasamples per second. So finally, we're going to introduce some gain blocks into the transmitter. And the reason we need the gain blocks is to give the optimum signal levels to the DAC and the mixers to give the very best performance in the radio. And finally, the gain control at the end here enables us to vary the output power without disturbing the setup of the rest of the transmitter. So for example, some systems such as GSM have power ramping requirements because they're a time division system, and sometimes the transmitters are operating and sometimes it switches off. The receiver is very much a carbon copy of the transmitter, but with the signals in the reverse flow direction. So we have an image rejection consideration in digital radio. The positive and negative frequencies are quite different from each other, and they have different behaviors. So this means that any leakage of the positive frequencies into the negative frequency bandwidth looks like a degradation of signal to noise. So to deal with this, the LimeSDR has calibration modes, and we can calibrate for this image rejection problem. We typically achieve 50 dB image rejection when we calibrate. So again, in the receiver we have issues with aliasing. So we have again a sampled system, and we need to constrain the input bandwidth to only the sample frequency which we're interested in. Otherwise the ADC will receive signals in multiples of the sample rate. The problem is so severe that if we introduced a signal that is at an alias, we cannot differentiate it in the receiver from the intended signal and its alias. So again, we use oversampling to manage the adjacent channel interference issues that go along with a with a 0 IF receiver. So a common figure of merit is adjacent channel rejection. And by using analog filtering before the ADC, we can achieve some level of adjacent channel rejection. And also by using oversampling, we're able to improve adjacent channel rejection. The receiver, like the transmitter, uses 0.5 dB ripple Chebyshev filters. This time they're third order, with the real pole in the TIA stage and the complex pole in the LPF stage. And the ratio of these two defines the level of filter ripple. Again, like the transmitter, the receiver has optimum receive levels. So we have a variable gain low noise amplifier to control the level reaching the mixer. And then we have an IF gain control, which defines the level reaching the ADCs. And by carefully selecting these, we can get the best performance out of the transceiver. So now let's have a look at phase noise. We have phase noise producing problems from two different areas. One is from the transmitter, where out-of-band noise from quantization and from the active filters leads to noise in the receive band, even if the receive band is at a different frequency to the transmitter. This is coming primarily also from far-out phase noise as well as the quantization and filter noise. And these can deafen the receiver, particularly if the transmitter has been amplified by a high-powered amplifier. So there are two approaches for dealing with this. The first is time division duplexing, where the transmitter transmits in a certain period of time, and then the receiver operates in a different time period. And the other is frequency division duplexing, where the transmitter transmits at one frequency and the receiver transmits at another frequency. And we give an example calculation here for a duplex filter with 50 dB isolation and a 25 dBm transmit output power, showing that the received phase noise is comparable to the thermal noise of the receiver. So here's a measured response of a SAW filter. I think this one's for 800 megahertz bandwidth. And as you can see, we're getting something like 50 dB isolation between the two channels. The SAW filter is essential for good performance of the radio. So let's have a look at the receive phase noise problem. In the 3G and 4G specifications, there's a particular blocker requirement that demands very high dynamic range in the receiver. So typically you'd have a minus 15 dBm CW blocker signal at a 20 megahertz offset from the edge of the receive band. And we can split the noise of the system into different parts. So we have the thermal noise of the LNA and of the environment. And then we have the far out phase noise of the receive synthesizer, which modulates onto the CW blocker. And then we have our wanted signal. So again, we can do some very simple calculations. With a 20 dBm input signal, we're assuming that the filter is reducing the input signal by 5 dBs. And with 155 dBc phase noise, that's coming out at about 175 dBm per hertz. And our thermal noise is about 170. So we're losing about 1 dB of sensitivity in the receiver when the CW blocker is present. Okay, the receive band also has third order intermodulation properties, and these are different depending on whether the interfering signals are in band or out of band. In the case where the signals are in band, the performance is very much sensitive to gain, whereas the outer band second and third order intermodulation performance is largely defined by LNA gain. And we typically achieve something like +5 dBm third order intercept point and 48 dBm IP2 performance. So now let's have a look at the digital half of the Lime 7002. I think it's possibly even more complicated than the analog part of the receiver. So on the transmitter we have the data coming in at this end, going through some general purpose FIR filters. They are then interpolated, I'll explain that in a moment, frequency translated with a digital mixer, then going through an inverse sync function, and then through amplitude and phase correction for image rejection, and DC offset cancellation. And the receiver likewise is the opposite flow. We initially go in through image rejection, phase and amplitude correction, DC offset correction, digital down conversion, decimation, and then general purpose FIR filtering with a digital automatic gain control and signal strength block. So why do we need some of these blocks? So inverse sync corrects the behavior that occurs in sample and hold systems, which means that as the signal approaches the sample rates, the signal tends to peak. So basically it's just a digital filter. Quite often we want to transmit at a rate that's slower than the actual final ADC and DAC clock rates. So we use a technique called interpolation and decimation. Basically this is a combination of upsampling and filtering. So for example, you take a sequence of points and you insert zeros in between them and then filter, and this gives us the upsampled frequency response. And likewise we can do the same with the receive path, filtering and then subsampling. So on-chip decimation interpolation means we can trade between the interface speed and the actual oversample rates we use on the ADC and DACs. The general purpose FIR filters are generally intended to be up to 160 taps, although frequently there's less taps available if you use lower rates of decimation and interpolation. They're usually low pass, though of course you can design them to be high pass or band pass. And the filter coefficients can be easily calculated using Octave or MATLAB. The baseband also comes with a numerically controlled oscillator, which can be used for low IF transmit and receive or frequency hopping. We also can use it for developing test signals for calibration, for example calibrating the filters and also calibrating image and LO leakage in the transmit and receive paths. Additionally, there's an AGC block designed for repeater applications and a receive signal strength for calibration and for controlling the AGC. The digital block also includes an 8051 based microcontroller which we use for running the calibration software. The LimeSuite GUI gives us access to all the registers on the LMS 7002, and these are grouped into the A and B channels for the MIMO, and is divided into a number of tabs, for example calibrating the SDR, the RF front end for the receiver, the RF analog baseband for the receiver, the RF transmit path, the RF analog baseband, the data converters, overall bias, internal regulators, the buffer for the crystal reference, the clock generator for the baseband digital, the transmit and receive synthesizers, the digital interface, the signal processing blocks we just discussed, as well as various other auxiliary control tabs. So, tips on using the LimeSDR well. I think one of the most important ones is to start from a well-defined working set of initialization file. So we give example files for different applications, and then using the FFT viewer and our loopback configuration, you can then optimize the settings of the radio for your particular application. Make sure there's some sort of frequency planned for clock frequencies. For example, you don't want the clock frequencies interfering with your signal. You also want to set up with best dynamic range. So this frequently means using the minimum amount of gain required to achieve your sensitivity. The temptation is to use as much gain as possible, but this gives you poor tolerance to interference signals. Use RF matching for the transmit and receive to get the best output power and the best noise performance and best matching. Typically, the RF receiver matching is a little away from the S11 match to give the best noise figure. Typical settings would be for the LNA with max gain -9 for the LNA, TIA on maximum gain, the PGA on 0 dB gain, and a clock gen of about 250 megahertz. We did an example for a Sat-nav application. This used an external antenna which contained a LNA and a SAW filter, and then this came into the analog part of the 7002, and we configured the LNA for maximum gain, though that's not strictly necessary. We had a 3 megahertz low-pass filter, and we had the variable gain IF amplifier at maximum gain. The synthesizer was tuned to 1573 92 megahertz. The clock gen was set up with 261888 megahertz, with the ADCs running at 65 megasamples per second, using image rejection cancellation. We then used the digital down converter running at 1.5 megahertz to produce the low IF signal. We then used times 32 decimation and a 29 tap raised cosine filter to do the pulse shaping. And then finally we transmitted it to baseband at 2 megasamples per second. Just a few words about the FPGA on the LimeSDR. The FPGA provides the interface between the USB controller and the 7002 radio. This provides playback of waveforms as well as FIFO storage. So, can I alter the FPGA? Yes. The FPGA has a number of resources, including 116 18-bit multipliers, 4 PLLs, about 39,000 gates, and about 1 megabyte of RAM. You can get the Altera design tools for the Cyclone 4E from the internet, and you can get the code for the LimeSDR interface from the Myriad-RF webpage. And then it's just a matter of using the Quartus design suite with VHDL or Verilog or schematic and IP blocks. Design your test benches in VHDL or Verilog. Do a logic synthesis and simulate using ModelSim, and then carry out a place and route synthesis, and do a timing analysis and then download to the SDR.